Hello all, welcome to your 5-5 flip video. 5-5 is operations with rational numbers. So really this is just applying PEMDAS to the rational numbers. Now what are the rational numbers? Well, let's do a quick review. You have the natural numbers, 1, 2, 3 all the way to infinity. Around that you have the whole numbers, 0 plus the natural numbers. All whole numbers are also integers, so these are the negatives, -1, -2, -3, all the way down to negative infinity, plus your whole numbers, and then around that you have the rational numbers, all right? And rational numbers can be written as a over b or negative a over b, and you'll remember from 5-4 that the reason we can do negative a over b is because we know that negative on the outside of the fraction a over b is the same thing as negative a over positive b, which is the same thing as positive a over negative b. Those three things are all the exact same thing. So it doesn't matter where the negative is in the fraction, as long as there's only one negative, the whole quotient, the whole system is going to be a negative number. So you can write it as negative on the outside, and you account for all of those scenarios, all right? Really quick, PEMDAS, you guys know that. Please excuse my dear Aunt Sally. What does that stand for? Parentheses, exponents, multiplication, division, addition, subtraction. You do these, this is the order of operations, from left to right, from category to category. So you always start at the left of your equation, do any parentheses, and then keep going down your equation towards the right. If you see another parentheses, then do those. Once all the parentheses are done, you go back all the way to the left, look for any exponents, and do the process again and again and again, moving from left to right for each category, all right? Now, we have to review the distributive property, and you've been exposed to this, whether or not you remember it. And this, I'm going to show it to you, and then we're going to make the algebra that goes with it. So if you have the expression a times the quantity b plus c, so b plus c is in parentheses, and a is being multiplied by the whole quantity, you can distribute that a. Now let's look at it as if you use PEMDAS, so let's look at just a very simple example. 2 times the quantity 1 plus 3. PEMDAS tells me I should do parentheses first, so that 1 plus 3 turns into 4. So this whole expression turns into 2 times 4, which is 8. Now if I distribute first, what I do is I apply that times 2 to all of the components inside the parentheses. So I apply the times 2 to the 1 and the times 2 to the 3, and then solve afterwards. So I can distribute that 2 to the 1, so it's now 2 times 1 plus, and the reason it's a plus sign is because it's 1 plus 3 and not 1 minus 3, or 1 divided by 3, or 1 multiplied by 3. So whatever symbol is there, you keep. So 2 times 1 plus 2 times 3. Now I just use PEMDAS, go left to right. 2 times 1 is 2, 2 times 3 is 6, 2 plus 6 is 8. So we get the same answer, and what does that tell me? It tells me that the distributive property is just as valid as a methodology as is PEMDAS, the order of operations. So I can rewrite a times the quantity b plus c to a times b plus a times c. And this works for however many categories of numbers you have inside the parentheses. If you have a times b plus c minus d plus e plus f minus g, that's the exact same thing if you distribute them all across as a times b plus a times c minus a times d plus a times e plus a times f minus a times g. So notice I keep all of these other order of operations symbols in my equation. I'm just distributing to the a. I'm not changing the relationship, I'm just changing the order I would do it in. I'm distributing first versus solving everything in the parentheses and then solving. Okay, so let's look at an example. I'm also going to put a negative in red under these pluses because, again, it's plus or minus. Really, it's plus minus. I'll add in multiplication and division as well. We'll do a worksheet on this to help clarify, but you keep whatever symbols are there. So if you have the equation 2.1 times the quantity 1.2 minus 3.6 plus 4.4, and you have to solve this through the distributive property. If you distribute that 2.1, you get 2.1 times 1.2 minus, because it's originally a minus sign, minus 2.1 times 3.6, and then that 4.4 is not inside your parentheses, so you're going to leave it alone on the outside by itself, so plus 4.4. So if you do PEMDAS left to right, 2.1 times 1.2 is 2.52, minus 2.1 times 3.6 is 7.56, plus 4.4. Now it's just an easy adding, subtracting decimals type question. 2.52 minus 7.56 left to right, negative 5.31 plus 4.4 gives me negative 0.091. If you did PEMDAS, solved the parentheses first, then multiplied, then added the 4.4 at the end, you would get the exact same answer. All right. Now, part of 5.5 is changing numbers from Fahrenheit to Celsius. Fahrenheit is the temperature system we use in the United States and several other places of the world. Celsius is what most other countries use to tell temperature. It's just a different system. Scientists also have a third system called Kelvin. Maybe that'll be an extra credit question or something that we do a little bit later on, but Kelvin is the third as the most scientific means of measuring temperature. But you can convert between Celsius and Fahrenheit pretty easily based on these equations. So Fahrenheit is 9/5 times the degrees in Celsius plus 32. If you do some algebra and rearrange, you can get C by itself and get C is equal to 5/9 times the quantity F, the degrees in Fahrenheit, minus 32. So what we're going to do is we're going to practice one of each. And if I tell you Celsius is 10 degrees, what's the temperature in Fahrenheit? And if Fahrenheit's 90 degrees, what's the temperature in Celsius? So let's start with the Celsius is 10. So I'm going to take the Fahrenheit, because I already have Celsius, I want to know Fahrenheit. I take that equation, and I plug in 10 for the Celsius spot. Now, if you only knew one of the two equations, you could do the same thing for the other equation and say 10 is equal to 5/9 F minus 32, and then solve for F. But I feel like that's a little bit hard for some of you guys, and it's a little bit more work. So just pick the equation that is easier, and for you guys, if you know what C is, pick the one where F is by itself already, so you don't have to do any rearranging. Excuse me. So F equals 5/9 times 10 plus 32. So all I did was I took the 10, I threw it in there for C, because C is equal to 10. Now I just solve. So PEMDAS, left to right, 5/9 times 10 would be the first thing I do. So I'm going to turn everything into a fraction just to make my life easy. So I have 5/9 times 10 over 1, which is 9 over 5, plus 32 over 1. Now, some of you may have forgotten, when you add or subtract fractions, you need to have common denominators. So I see my 90 over 5 has a denominator of 5, and then the 32 over 1 has a denominator of 1. It's much easier to scale up than to scale down, I think. So what I'm going to do is I'm going to turn that into 90 over 5 plus 175 over 5. And how did I do that? I did 32 times 5 and 1 times 5 to get 175 over 5. So then I have common denominators of 5. Now it's just a simple addition problem of fractions. 90 plus 175 gives me 256. The denominator stays the same in adding and subtracting fractions. So 265 over 5, which is 53. So if 10 degrees Celsius is equal to 53 degrees Fahrenheit. So clearly I'm out of room, so let's go to a new page. So I'll rewrite the equation. C equals 5/9 times the quantity F minus 32. So if F is 90, how do you solve this? Well, you take that equation, you plug in 90 for the F, because F is equal to 90, and then you solve. So let's look at it. I'll solve it both ways, using the distributive property and PEMDAS. Let's first look at PEMDAS, so parentheses first. C equals 5/9, 90 minus 32 is 50, so, 58. So 5/9 times 58, so I'm going to change it all to fractions. 5/9 times 58 over 1, which gives me 290, because 5 times 58 is 290, 9 times 1 is 9, so 290 over 9, which gives me 32 and 8/9 when you put it into a mixed number. All right, now what if I didn't want to do that? What if I want to use the distributive property? Well, same initial process. I'm still plugging that 90 in for F, but now I'm going to distribute that 5/9 to the 90 and that 5/9 to the 32. So I get 5/9 times 90 minus, because we originally had a minus sign, so minus 5/9 times 32. I'm going to change everything to fractions just for the sake of simplicity. So 5/9 times 90 over 1 minus 5/9 times 32 over 1, which gives me 5 times 9 is 450, 9 times 1 is 9, minus 5 times 32 is 160, 9 times 1 is 9, so 450 over 9 minus 160 over 9. It's nice because our denominators just happen to both be the same number, so I don't have to do common denominators, because this is a subtraction of fractions problem. So 450 minus 160 just gives me 290. Denominator stay the same, so 290 over 9, which just goes to 32 and 8/9. All right. Now, there's another way you could have gotten to this answer, and if you go to this last step down here and do 450 over 9 minus 160 over 9, what you could have done instead would be to simplify. So 450 divided by 9 is 50, and 160 divided by 9 is 17 and 7/9. So it's really 50 minus 17 and 7/9, which can also simplify down to 32 and 8/9. I feel like that's a little bit more work, because then you'd have to find common denominators, so 50 over 9. It's really the same process. Do whatever makes your brain work, okay? Now, I'm not going to say distributive property or PEMDAS is better. They're just different ways to get to the same end result, because they're equally valid, all right? Last thing we're going to talk about is complex fractions, and really, you're never going to leave a complex fraction as an answer unless explicitly asked to do so. It's because mathematicians hate complex fractions. A complex fraction is a fraction within a fraction. So an example would be having a fraction in your numerator and a whole number in your denominator, so like 1/2 over 10. Or a whole number in your numerator and a fraction in your denominator, so like 3 over 1/5. Or a fraction in the numerator and the denominator, so like 8 over 9 over 7 over 6. They're just ugly fractions. They're really hard to work with, and we need to know how to simplify them. So really quick, just as a reminder, a fraction is just a division problem. A over b really means a divided by b. So we can use that information to simplify complex fractions. So a over b is equal to a divided by b. So if I have the fraction 1/2 over 3/4, that really means 1/2 divided by 3/4. And you guys know how to divide fractions. That's easy. Keep, change, flip turns into 1/2 times 4/3. 1 times 4 is 4, 2 times 3 is 6. And you can simplify 4/6 as 2 over 3, and then you're done. So 1/2 over 3/4 can really be simplified to the fraction 2 over 3. So you just have to remember to find your big, I don't want to say the big fraction bar, but the main one, the important one, the one that divides the numerator of the entire fraction over the denominator of the entire fraction, and then replace it with a division sign. So find the big fraction bar, and then, sorry, I lost my train of thought. Just find the big fraction bar and replace that fraction bar with a division sign, and then it's just two fractions divided by each other, and you can do that. All right, so we'll cover this more explicitly in class, but as long as you can do the distributive property, PEMDAS, and complex fractions, you're fine. That's really the heart and soul of 5.5. 5.6 will be taking this one step further into more complex problems, so we'll worry about that when we get there. But as I think the main things you should be able to get out of this is distributive property, complex fractions, and then using them appropriately to solve different problems. Let me know if you have any questions.